We're in Rosen, Discrete Mathematics and its Application, section 9.5 on equivalence, relations, and classes. Here we define equivalence class. First we start with an equivalence relation, R. Remember, an equivalence relation is a relation that is reflexive, symmetric, and transitive. On the set A, we say that all elements related to a specific element A are called the equivalence class of A. We have a symbol for that. It's the A enclosed in brackets. And if needed, we will reference the relation, but if we only have one relation in mind, we can drop the R. And one way to write this would be the equivalence of class of A with respect to R is a set of all elements S such that AS is an element of R. We can take other elements from the equivalence class, any one of them, we'll call it B in this case, and we say that it is a representative of the class. Indeed, A could be called a representative of the equivalence class. Any element could be. All right, here's an example. Again, we'll look at congruence classes modulo M. And the congruence classes modulo M are those elements when you take the difference of them, the remainder is divisible by M. So if A is an element, then A plus M is an element, A plus 2M is an element, A minus M, A minus 2M, and so forth, because the difference of any of these two elements results in a number that is divisible by M. Here is the equivalence class modulo 4 for 0. And notice that every element, if you take the difference of any two of them, it'll be divisible by 4. The equivalence class of 1 modulo 4, once again, if you take the difference of any two of these, then it'll be divisible by 4, or another way to state it is every one of these has a multiple of 4 difference between them. There's also an equivalence class of 2 modulo 4 and an equivalence class of 3 modulo 4. So 4 equivalence classes on the set of integers modulo 4. Excuse me. Okay, theorem 1. We have some things we can state about these equivalence classes under a relation on a set A. All of these three statements are considered equivalent. A is related to B under the relation. The equivalence class of A is equal to the equivalence class of B. And the equivalence of class of A intersected the equivalence class of B is non-empty. We're going to do a quick proof of the first one implying the second one. So we have 1 implies 2. In the book, you'll see that 2 implies 3, and that 3 implies 1. Okay, so 1 implies 2. Assume that A is related to B. Now we'll pick a representative of that set C. We know that A is related to C because they're in the same equivalence class. And we were given that A is related to B. And since R is symmetric, B is related to A. And now by transitivity, I have B related to A and A related to C. Transitivity gives me B is related to C. So C is a subset of the equivalence class of B. So I started with C being a subset of the equivalence class of A. I showed that C is a subset of equivalence class of B. That means that A is a subset of B. And we could have done that same analysis in the other direction to show that B is a subset of A, which lets us conclude that the equivalence class of A is equal to the equivalence class of B when A is related to B. And I'll point you to the text for the other proofs. Okay, a partition of a set. I mentioned that word earlier. What is a partition of a set? Well, it is a collection of disjoint, non-empty subsets of S that when they're unioned together give us S. Here's a nice illustration of a partition using a Venn diagram where the subsets are the A sub i's. All right. In other words, it's a collection of subsets forms a partition of S if and only if I is the index set, by the way. Every subset is non-empty. If the indices are different, their intersection is the empty set. That's what disjoint means. And the union of all of them gives us S. So no non-empty sets, non-equivalent indices make the partitions disjoint, and their union makes the whole set. We're going to show here that an equivalence relation is a partition of a set. So R is an equivalence relation on the set A. The union of all the equivalence classes is all of A, since an element of A can be its own equivalence class. So every element could be its own equivalence class, and since that's the case, the union of every equivalence class of A will give us A. And then from that earlier theorem, we saw that equivalence classes are equal or disjoint, so that if they're disjoint when they're not equal, which is how a partition works, and therefore the equivalence classes form a partition of A because they split A into disjoint subsets. Okay. All right. So theorem 2 actually extends this. So R is an equivalence relation on S. Given that the equivalence classes of R form a partition of S, and conversely, given a partition of the set S, there's an equivalence relation that has that partition as its equivalence classes. So in other words, an equivalence relation is a partition, and every partition is an equivalence relation. So we've already shown the first part of the theorem on the previous slide. For the second part, we're going to show that all partitions are equivalence relations. We assume that this is a partition of S, A sub I, where I comes from the index set as a partition. And then the relation will be the set of pairs of X, Y, where X and Y belong to the same subset in the partition. And we'll show that this satisfies the properties of an equivalence relation, namely reflexivity for every A element of S. AA is in R because A is in the same subset as itself. Symmetry, if AB is in R, then B and A are in the same subsets of the partition, so BA is also in R. And then transitivity. If AB is in R and BC is in R, A and B are in the same subset, and B and C are in a common subset. Since these are subsets of a partition, they're either identical or disjoint. B belongs to both subsets, so the two subsets from the partition must be identical. Therefore, AC is in R, since they belong to the same subset of the partition.